New video just coming in showing Ukraine's bold drone strike on Russian aircraft.
It is the first time in 3 years that the defense secretary won't be at this meeting. What is your reaction to that?
Russian artillery now so close, they are striking the city centre. At least 4 civilians killed, about 20 injured Tuesday. Ukraine's strategic moonshots definitely a boost for morale and a hint they still have some hidden cards to play. But this, as Putin seems intent to ignore President Donald Trump's calls for a ceasefire.
At 0612 hours on June 1st, 2025, 24 Ukrainian drones flying just 300 feet above the tundra breached Russia's defences. In a matter of minutes, these drones dismantled what was considered one of the most advanced air defence systems in the world. The S-400 and Pantsir, systems valued in the billions. But how did this strike succeed against technology designed to be impenetrable? Today, we reveal the tactics and technical insights behind this operation. We'll explore how Ukraine combined clever strategy with fundamental physics, exploiting radar horizons and minimum missile arming distances to turn Russia's premier air defences into liabilities. The S-400 Triumph is advertised as Russia's most formidable air defence system, capable of tracking up to 300 targets and engaging threats at ranges of up to 400 kilometers with its 48 N6E-3 missiles, which can strike targets as far as 250 kilometers away. Its radar suite, including the NEBO-M and X-band engagement radars, is designed to detect and neutralize everything from ballistic missiles to stealth aircraft. Yet, this reputation did not account for a precise understanding of physics and the operational envelope exploited by Ukrainian forces. Instead of confronting the S-400 head-on, Ukrainian drones sidestepped its strengths by flying at just 300 feet above ground level. At this altitude, the Earth's curvature created a radar horizon that dramatically reduced the S-400's detection range. While the system boasts a nominal reach of 400 kilometers, the effective detection range against these low-flying drones shrank to around 40 kilometers, barely a tenth of its advertised capability. This meant that the drones remained invisible to the S-400's ground-based radars until they were already well within striking distance. The NEBO-M radar, optimized for tracking large, fast-moving targets, struggled with the small radar cross-section and slow speed of the drones. Its VHF beam, hundreds of meters wide, could detect an object the size of a drone, but lacked the positional accuracy to guide an interceptor missile. Meanwhile, the X-band engagement radar, operating at higher frequencies for precise tracking, encountered significant ground clutter. Rocks, buildings, and terrain features reflected radar waves, masking the drone's signatures and making positive identification and tracking difficult. The combination of these technical limitations left the S-400's operators with only a fleeting window to react. But detection was only the first challenge. The S-400's missiles, while advanced, require a minimum distance of 2 kilometers to arm their proximity fuses and achieve aerodynamic stability after launch. Ukrainian drones moving at 50 meters per second could cross this gap in about 40 seconds. And this left Russian crews with less than a minute to detect, identify and engage the drones, an interval far shorter than the system's ideal engagement cycle. Even when the search radar of the nearby Pantsir system detected the drones at 4 kilometers, the reaction window was reduced to just 2 seconds, insufficient for a coordinated missile launch. The result was a rapid sequence of events. By 6:14, the lead drones had already slammed into the gravestone radars, blindfolding the S-400 in under 2 minutes. With its eyes destroyed, the system's launchers and control vehicles became exposed targets. The attack continued, with additional drones homing in on the now defenseless launchers and nearby aircraft. The aircraft stationed at Oenia Air Base, intended as a regional air operations hub, were destroyed before Russian crews could mount an effective response. This operation demonstrated that even the most advanced and expensive air defense systems can be neutralized by exploiting physical limitations and tactical timing. The S-400 was designed to repel high-speed jets and coordinated missile barrages, not slow, low-flying drones that leverage the radar horizon and minimum engagement distances. The Ukrainian approach exposed a critical weakness. The system's technical sophistication could not compensate for the immutable laws of physics or the constraints imposed by its own safety protocols. The implications for modern warfare are clear. Highly networked, multi-billion-dollar defense systems remain vulnerable to adversaries who understand their operational limits and are willing to innovate. The Ukrainian strike did not rely on overwhelming force, but on a detailed understanding of how radar, missile arming, and timing interact under real-world conditions. The result was not just the destruction of equipment, but a demonstration that adaptability and precision can outweigh brute technological superiority. Yet this was only part of the equation. The Ukrainian operation also revealed that the environment itself could become a decisive factor in battle. As the action shifted north to Oenia Air Base, another set of vulnerabilities emerged, not in the circuitry of Russian air defences, but in their ability to withstand the unforgiving Arctic cold. At Oenia Air Base, the main threat to Ukrainian drones came from the Russian Pantsir S-1 air defense systems. These units, designed for close-range protection with twin 30mm autocannons and surface-to-air missiles, faced a new adversary: Arctic cold. As temperatures dropped to -12 degrees Celsius, the Pantsir's hydraulic systems began to fail. Turret traverse rates, normally 60 degrees per second, slowed to under 20. The autocannons, built to fire 5,000 rounds per minute, jammed as lubricants thickened, dropping to around 1,000 rounds per minute. These mechanical failures dramatically reduced the system's ability to track and engage the incoming drones. Missile performance suffered as well. The Pantsir's proximity fuses, which rely on capacitors and oscillators calibrated for room temperature, malfunctioned in the extreme cold. At -12 degrees Celsius, electronics drifted out of specification, causing missiles to pass directly through drone formations without detonating. The result was a defense system unable to respond quickly or effectively as the attack unfolded. In contrast, Ukrainian drones operated without interruption. Lithium iron phosphate batteries powered their simple brushless motors, maintaining full output despite the sub-zero conditions. The drone's design avoided the mechanical complexity that left the Pantsir vulnerable. With no hydraulics to seize or lubricants to freeze, their systems remained fully functional throughout the operation. Thermal imaging provided another advantage. In the Arctic's cold, every heated building and fuel tank glowed like a lantern, a perfect bullseye for the drone's infrared cameras. Ukrainian operators used these signatures to target aviation fuel tanks and critical infrastructure with precision. The first strikes ignited fuel reserves, triggering explosions that reached temperatures of 2,500 degrees Celsius. Steel, already chilled to -12 degrees Celsius, fractured under the sudden thermal shock, producing a fragmentation effect that sent shrapnel across the base. Fires spread quickly, and the destruction was visible from space. Russian defenders attempted to counter the assault, launching over 40 Pantsir missiles and firing thousands of rounds. Despite this effort, only 3 drones were intercepted. The majority of the drones reached their targets, highlighting the limitations of the Pantsir when faced with environmental stress and a resilient adversary. The P-18 spoon rest radar, a legacy system from the 1970s, added little to the defense. Its vacuum tube amplifiers became unstable in the cold, making it ineffective against small, agile drones flying at low altitude. This phase showed that weather and terrain can be as decisive as any stealth aircraft or missile. The Ukrainian approach at Oenia did not rely on overwhelming force, but on exploiting the operational environment. By understanding the effects of temperature on enemy systems and designing their own drones for resilience, Ukrainian forces neutralized a modern air defense network with minimal resources. The aftermath at Oenia demonstrated that even advanced technology can be rendered ineffective by conditions outside its design envelope. Russian operational timelines suffered as critical assets were immobilized. The destruction of the base underscored the vulnerability of over-engineered systems to environmental extremes and highlighted how adaptability and strategic timing can shift the balance in modern warfare. As Ukrainian drones withdrew from the burning airfield, the lessons of Oenia set the stage for the next challenge. The focus would shift from environmental exploitation to the complexities of integrated defenses, where swarm tactics would test the limits of Russia's most sophisticated air defense network. At Diagalev Air Base, the core of Russian integrated air defense was put to the test. The base's protection relied on overlapping S-400 batteries for long-range interception, Pantsir S-1 systems for close-in threats, and Kushuka electronic warfare units for signal disruption. This network was designed to present a seamless, multi-layered barrier against any aerial incursion. Yet the Ukrainian attack on Diagalev was not a test of brute force, but of distributed intelligence and emergent behavior. The operation began with 31 drones, split into 7 subswarms, each advancing from different directions, altitudes, and speeds. These subgroups continually merged and split, forcing the Russian fire control computers to recalculate intercept solutions in real time. Every shift in the swarm's geometry required the defensive network to restart its engagement sequence, introducing cascading delays that eroded the system's ability to respond. The drone's movement exploited a critical limitation in the S-400's engagement cycle. From detection to missile launch, the process took about 12 seconds. During that window, each drone, moving at 50 meters per second, covered 600 meters, repeatedly outrunning the intercept solutions before the missiles could be launched. The swarm structure ensured that at least one subgroup was always within the engagement envelope, keeping the defenders in a constant state of reaction and preventing them from mounting a coordinated response. The result was a defensive network overwhelmed by the tempo and unpredictability of the attack. Electronic warfare was the next line of defense. Russian operators activated all available Kushuka systems, saturating the airspace with jamming across every frequency band. The goal was to sever communications and navigation links between the drones, rendering the swarm ineffective. However, the Ukrainian drones countered with frequency hopping at 1,000 times per second, making it nearly impossible for the jammers to lock onto any single channel. This rapid switching preserved the drone's ability to coordinate and adapt. More than that, the drones used the intensity of the jamming as a navigation tool. The stronger the interference, the closer they knew they were to valuable targets. Russia's electronic countermeasures, intended to blind the drones, instead became a homing beacon that guided them to their objectives. The swarm operated on a mesh network, with each drone communicating through microbursts to share its position and status. This decentralized architecture eliminated any single point of failure. If one drone was lost, the rest continued seamlessly. Simple behavioral rules, maintain spacing, avoid collisions, converge on gaps, produced an emergent attack pattern that no centralized defense could anticipate or efficiently counter. The mesh network allowed the swarm to adapt in real time, responding to losses or changes in the environment without pause. As the assault progressed, the Russian air defense crews faced a relentless barrage. The S-400 and Pantsir systems struggled to keep up with the volume and unpredictability of the attack. Each engagement cycle lagged behind the drone's maneuvers, and the constant recalculation of intercepts created a backlog that the defenders could not clear. The psychological effect was immediate. Operators were forced into a reactive posture, unable to regain the initiative as the swarm pressed forward. The culmination of the attack came at 6:31. 17 drones struck Diagalev within a 2-second window, their explosive payloads landing in overlapping arcs. The resulting blast waves generated pressures exceeding 50 psi, powerful enough to collapse reinforced aircraft shelters and scatter debris across the base. Fires erupted as aviation fuel ignited, and key infrastructure was reduced to rubble. Half the base's operational capacity was lost in minutes, with several Pantsir and S-400 units destroyed. The complexity and redundancy of the integrated defences, once considered a strength, became a liability. Each layer introduced delays and points of confusion that the swarm exploited. This attack exposed a fundamental vulnerability in hierarchical, centralised defence networks. The Ukrainian drones, operating with distributed intelligence and emergent tactics, bypassed the strengths of integrated systems and capitalised on their weaknesses. Processing delays, decision bottlenecks, and technological rigidity. The destruction at Diagalev underscored a shift in modern warfare, where low-cost autonomous units could overwhelm systems worth millions through coordination and adaptability. In the aftermath, Russian crews and commanders faced a new reality. Traditional defences, reliant on speed, hierarchy, and signal denial, had failed against a threat that adapted faster than they could react. The lessons from Diagalev would echo in the next phase of the conflict, as advances in autonomy and artificial intelligence redefine the limits of precision and targeting. At Ivanovo Air Base, the Ukrainian operation advanced beyond traditional electronic warfare and into the realm of autonomous precision. Russian defences at Ivanovo relied on GPS jamming and an array of decoys, tactics that had frustrated previous generations of guided munitions. Yet, these countermeasures proved ineffective against a new adversary. AI-guided drones trained over 18 months on extensive satellite imagery. These neural networks did not depend on external signals or human oversight. Instead, each drone used real-time image analysis at 30 frames per second, matching live video feeds to a vast database of terrain features, roads, structures, and even subtle tree lines, allowing them to navigate visually, much like a person finding their way through a familiar city. As Ivanovo's GPS jammers flooded the airspace with interference, the drones remained unaffected. The AI recognized the layout of the base, cross-referencing every landmark against its internal dataset. The result was a guidance system immune to signal denial. While Russian operators increased jamming power, the drones continued their approach, recalibrating their position with each new reference point. The sophistication of this visual recognition process rendered Ivanovo's electronic defenses obsolete, exposing a fundamental vulnerability in strategies that relied on signal disruption. This autonomy extended to target selection. Ivanovo's defenders had deployed a network of decoys, false radar arrays, inflatable aircraft, and simulated heat sources, intended to misdirect attackers. However, the drones as AI, trained on thousands of images, used a multi-layered verification process. By comparing heat signatures, shadow angles, and antenna profiles against millimeter-exact models, the AI ignored inflatable decoys and locked onto real targets. No single detail escaped scrutiny. Even the alignment of shadows or the configuration of antennas could reveal a decoy. This autonomy set the stage for the sledgehammer blow to Russia's strategic bombers and fuel network. Mesh networking played a critical role in the attack's execution. Each drone operated as part of a distributed system, sharing burst transmissions of target data and engagement status with the rest of the swarm. When one drone identified a high-value asset, such as a hardened shelter or a parked bomber, the information propagated instantly across the network. This allowed the swarm to dynamically redistribute itself, assign warhead types according to target vulnerability, and coordinate attack angles to maximize damage. The drone's decision-making was entirely autonomous. No human operator intervened once the mission began. The attack unfolded with methodical precision. Drones armed with penetrator warheads targeted reinforced shelters, while others equipped with fragmentation charges focused on aircraft in the open. Those assigned to the nuclear, capable to 95 ms bombers programmed their strikes to hit structural weak points, such as wing roots and fuel tanks, ensuring maximum destruction. Simultaneously, a subset of the swarm targeted the underground fuel system, detonating explosives beneath the surface and igniting a base-wide fire. The resulting inferno disabled repair operations and destroyed critical infrastructure. Russian air defenses, including Pantsir systems and legacy missile batteries, struggled to adapt. Their fire control computers, already overwhelmed by the need to discriminate between real and decoy targets, could not keep pace with the swarm's coordinated maneuvers. As drones attacked from multiple vectors, the defensive network fractured. Attempts to redirect fire from decoys to genuine threats lagged behind the swarm's rapid adjustments. By the time the engagement ended, several Tu-95 ms bombers were destroyed, fuel reserves were burning, and Ivanovo's operational capacity was crippled. The operation at Ivanovo demonstrated a shift in the character of warfare. The drone's autonomy, shaped by months of machine learning, real-time visual processing, and decentralized communication, delivered an outcome that brute force alone could not achieve. Efficiency, adaptability, and precision replaced massed firepower as the decisive factors. The destruction at Ivanovo was not simply a product of advanced technology, but of a new doctrine. One where machines learn, adapt, and execute missions with minimal human input. As analysts reviewed the aftermath, it became clear that the defenses which once seemed formidable had been outpaced by innovation. The devastation at Ivanovo underscored that adaptability and technological advancement, rather than static fortification, now determine the balance of power. This conflict has revealed a pivotal lesson: the interplay of physics, Arctic cold, swarm tactics, and AI-driven autonomy can systematically dismantle even the most advanced air defenses. Each phase of Ukraine's campaign, exploiting radar blind spots, leveraging environmental extremes, overwhelming with coordinated swarms, and deploying autonomous targeting, expose vulnerabilities that rigid, centralized systems could not overcome. The AI-guided strike at Ivanovo Air Base stands as a clear signal that future warfare will be shaped by adaptability and machine intelligence. The question now: can tomorrow's air defenses adapt, or will they be outflanked by innovation again? If you found this analysis eye-opening, hit subscribe and leave a comment. What does this shift in warfare mean to you?